All right. So today is probably the last day. It's probably the last day that you would call that's like review-ish. Okay, this is sort of review of 21-26. So we've done the whole course in 2.5 weeks. Maybe 2 weeks. So talk about t-test today. So we know this, that talked about this last time, and you've known this before, that we can take a z distribution. To get a z distribution to standardize a bunch of scores, we just take the score, we subtract the mean, and divide by the standard deviation. They're just standard deviation units, right? So to find the probability of a given value of a variable, how many people have an IQ greater than X? And if the variable is normally distributed, we just plug the numbers into there, we look it up in a table. We're using that web tool I showed you the other day. That's all doable. And you end up with the probability of a certain score, or greater than, or a certain score, less than, whatever. Okay? As we talked about last time. Now, maybe you don't find this interesting. It's not, that's a sarcastic headline. So as interesting as that is, we're usually not dealing with individual scores. In fact, it's exceedingly rare whenever we're looking at data that we're caring about an individual score. How likely is an individual score is not a question we tend to ask. It comes up. It does. There are times, but it's really rare. Okay? Instead of knowing about distributions, we actually, we care about x bar. How likely is this mean to have happened? We don't really care about individual scores. Right? So, I can't even think of an example offhand where I care about an individual score. We don't tend to do case studies that often. So we care about the distribution of x bar, how likely a given mean is, not how likely a given score is. Right? Last time we talked about hypothesis testing, I said, look, how likely are these two means to come from the same population? Not how likely are these two scores to come from the same population. Okay? Make sense? So far, it's a subtle distinction in a way between the likelihood of a mean and the likelihood of a score. But it's the same kind of problem. The numbers don't know that they're means or that they're individual scores. Do they? The numbers are just numbers. My old stats prof in grad school in Spence used to say the numbers don't know where they come from. They shouldn't know. He wasn't putting on a Scottish accent either. He still has one. He's still alive. He's Scottish or something. I think he wrote me a letter of recommendation for this job. Yeah. Oh yeah, I think he did. So, how likely is a given mean from a distribution of a whole bunch of means? The other day I talked about flipping coins a whole bunch of times and then getting the average number of flips that were heads, let's say. And then we had a distribution of those possible means. This is the same thing, okay? And this is something that's exceedingly important. I will rarely, probably never in your time of me teaching you, have I told you I want you to memorize something exactly the way it's written. Do that now. Okay, so this, on the other hand, is really important. So I may very well ask you a question like, what is the central limit theorem? You are to parrot that back to me. It's like, you memorized some Shakespeare in high school. You can do this. Okay, and I will, of course, break it down, for you. Given a population with a mean mu and a variance of sigma squared, the sampling distribution of the mean will have a mean of mu sub x bar equals mu, and a variance of sigma squared over n. As n increases, this distribution approaches normal. And note the bolded part, no matter what the shape of the parent population distribution. I talked a little bit about this last time. So let's break it down to its constituent parts. given a population with a mean of mu. So the mean of the variable itself is mu. Okay, so if we're going to use an example here, we would say like IQ, because that's what we know, the mean is 100. Okay? That's what mu is. So a variance of sigma squared, and again in IQ we know that the variance is 225, standard deviation 15. The sampling distribution of the mean will have a mean of mu. In other words, mu of x bar equals mu. What do I mean by that? Okay, that's where it gets a little complicated. A sampling distribution is a distribution of all the possible values a statistic can take with a given number of observations. So a sampling distribution is a distribution of all the values a statistic can take with a given number of observations. I think so. A sampling distribution is a distribution of all the values, all the possible values a statistic can take with a given sample size. Or a given n, if you want to use that. So the other day I talked about sampling students in Algoma University for their height. And the mean height is mu, 170, I'm just guessing. That's probably off. I'm just going to make something up. And we're going to sample, let's say, 20 people each time. I sample 20 people. I then plot what that mean weight was, or sorry, height. And then I do it again. And I plot that mean. And I do it again. And I plot that mean. And I do it, an infinite number of times. I then get what's called the sampling distribution of the mean. So instead of values for x and probabilities along the x-axis, I now have values of x bar. So the mean, what this is saying is the mean of that sampling distribution, the mean of the sampling distribution of the mean, is going to be mu. Okay. Actually equal mu. So it's going to be here. I'm also going to get other scores. Like I said, sometimes I'm going to sample, for some reason, I'm just going to get the men's and women's basketball teams. There's 20 people. Just people from there. And the height's going to be a little high. And then sometimes I'm going to get the not men's basketball team and women's basketball team, and it's going to be small. But usually, I'm going to get a mean of around, in fact, exactly. The mean I most expect to get is the same as the actual population mean for x for height. Okay? I know it's odd thinking of a distribution of a mean distribution for a bunch of means. But you have to realize, as I said, the numbers don't know where they come from. They're just numbers. Okay? So far, does that make sense? That's okay, right? Name is allergic to it, but beyond that, thank you. Makes sense. Okay, we're good. Now, it will have a mean and a variance of sigma squared over n. There's a variance of the heights of students here. I don't know what it is. We could make up a number. Let's say it's 10 centimeters. 10 says 100 for variance. So standard deviation 10, variance is 100. I don't know if that's true, but we can pretend. So if we're sampling, what I said, 20 people each time, then the variance of that sampling distribution is going to be 100 over 20 in this case, which is going to be 5. And it's going to be normally distributed. That's supposed to be completely symmetrical and normal. I know it isn't, I can't draw it. So it's going to be normal. We talked the other day about doing this flipping the coins as a sort of a thought experiment. Even with a binary variable, you end up with a normal distribution. You can prove this to yourself if you have some free time, which I know students are full of free time. If you have a die, Roll the die 10 times, get the mean. Do it again. So do this maybe 20 times. Again, this is if you have free time and you don't believe me. So roll it 10 times, and plot the mean of each of those 10 rolls, and do that 20 times, 30 times. You'll actually get a normal distribution, because that's how the universe works. Or if you're writing, code, you could probably do that simply. There probably are simulators online you can probably play with, like Google. It might take you less time, and it's a little more dramatic when you do it yourself. And that's what a die is uniform distribution. 6 possible values, yet you're going to get a normal distribution of means. The sampling distribution of the mean will be normal, no matter what the shape of the parent population distribution. That's really neat. There is a proof of it, as I said, it's frankly I've forgotten it. It's pretty advanced math for most of us, so I'm not going to worry about it. Mostly because I've forgotten it. But also, it wouldn't impress you if I just did a proof of it. Should be. I bet if you looked up the central limit theorem on Wikipedia, it would give you a proof. Go ahead. You want to do that? Have fun. So first off, do these properties here, so it's telling you what? The important properties of a distribution. The mean, the variance, and the shape. Does this make sense that it's telling you these 3 things? Do you see how it's telling you these 3 things? What these words say? That's the first one. Okay, that's the first question. Second question. Does it make intuitive sense to you? I think the mean probably does. I think the shape probably does, because you can sit there, when we talked about flipping coins the other day, you can imagine how that would work. Does the variance part make sense? That's usually the part where people go, well, how do you know the exact value?
Can you go into that?
I can. And as I said the other day, it's cool. Well, backing up, it's going to depend on the sample size. The variance is going to get tighter and tighter off the values, possible values of a mean, the more subjects you have, the more observations you have. If you have just one, let's talk about a completely ridiculous sample size of 1. The variance would be, well, it would be the same as the variance. It would be, because what you're doing, you're actually just doing individual scores and calling those means. Right? 160, 152, 171, 168, 103, 290. That's nobody that tall here. There's anybody that tall anywhere. But there's people that are 200 something. You see the men's basketball team, there's some big guys on there. Okay. We get all the scores, we'd actually get the distribution of scores. The variance would be exactly the same as the variance of the population. On the other hand, if I took, and the bigger it gets, the bigger n gets, the smaller the variance of the sampling distribution is going to be. Right? Because it's getting tighter and tighter. What if I sampled everybody all the time? Every possible person, all 1,200 of you. I would get the same score all the time. I wouldn't have a distribution of ever a point. What's the variance of a point? It's 0. Because you get the same score every single time. So the bigger n gets, we know that as n gets bigger, the variance of x bar, which is the variance of the sampling distribution of the mean, gets smaller. And we know it's related to the variance. Gotta be. And if it gets smaller, the bigger n is, well, it's got to be then divided by n. Because as n gets bigger, as n approaches infinity, take the limit of it, as n approaches infinity, variance of x bar approaches 0. more, how did this shoe come untitled? The more subjects you have, the smaller trust that shoe. The smaller the variance of the sampling distribution will be. Okay. Until you actually sampled all of them, and then the variance becomes 0. You never do that in practical terms because we're dealing with things that are so large that it doesn't matter. And if you could do that, you wouldn't do statistics because you're doing populations and then that. Okay. This is an important thing, and one of the neat things about this, can I move on from this, or you still have more questions? Because I can answer more. Okay. So this is really a powerful thing, because the population shape doesn't matter, because we know the shape of the sampling distribution to be. That's an amazing thing. I don't have to know the population shape, because I can know the shape of the sampling distribution by the central limit theorem. What matters here is, in fact, that you're randomly sampling observations. Now that I've tied this shoe, see what happens is this shoe doesn't feel tight enough, and now I've got to tie it because I like it to feel symmetrically the same tightness, because I'm really strange.
So if I pointed out that they weren't laced all the way up one?
Oh, but I don't want to waste all the way up.
One is.
Oh, that's why it's when you're done. No, I'm not going to go through that right now.
Okay.
It's going to bother me, but I'm not going to waste class on doing it. Believe me, it's going to bother me. So random sampling matters, but not nearly as much as you would think. People think that, in fact, you hear a lot about, oh, it's not a random sample, it's not a random sample, it's not a random sample. And when you do work called Monte Carlo experiments, which are just simulations, and you do enough of them, it turns out that random sampling matters, but not that much. Like so little that we can kind of ignore it. Which is great, because the math behind this assumes random sampling. That's why the math works. But in practicality, you can do it and say, yeah, it's pretty damn close, so close that we don't have to care. So when we randomly sample subjects, and everybody here's taking intro psych, and y'all participated in experiments, right? What's that?
A long
time ago, same here. Yeah, 1984 and 5.
Not that long ago.
Well, it was for me because I'm old.
I existed then, if that makes you feel better.
It's like how I existed when the fictitious advertising firm Sterling Cooper Draco Price existed. I'm so into Mad Men's Exterminator. I actually have a Mad Men advertising company. I'm so proud of it. Things you can find on Amazon. I'm so happy when it arrived yesterday. Drop ship from China, right? Made by political prisoners, probably. Okay, I hope not. That's all I'm saying. So, we all did that, and sometimes people criticize intro psych experiments or psych experiments in general and say, well, they're not representative, how can they do statistics? Firstly, representative is another thing, but even internal validity, how can you do statistics? It's not a random sample. In fact, the answer is, it really doesn't matter, which is great. Even though the math says it matters, practicality says it really doesn't matter. The central limit theorem is really robust when it comes to violations of the assumption of a simple random sample. Okay. It's not just not a representative sample intro psych students. Right? Look around the intro psych class here. More women than men, whiter than the average person in the population, more educated than the average person in the population, all that stuff, that's all true. But it doesn't affect the shape of the sampling distribution. It's really cool. So it does matter, but it's not something you should ever be concerned about. So to find the probability of a mean, and this is what we're going to be interested in, the probability of X bar, we're just going to use, how do we find the probability of a score? Well, we're going to use our old friend, the Z-score. So the Z formula changes a bit. In an intro stats, you're told, here's how you do a Z test. And in fact, and you're kind of taught that this is a whole new formula to learn, and it really isn't. It's all from the same place. So it's a score minus a mean divided by the standard deviation. Well, the score now is a mean minus a population mean divided by the standard deviation of the sampling distribution, which, well, is sigma over root n. So it's not anything different. We're just subbing stuff in for x is now x bar, sigma is now sigma over root n. Okay? That's all we're doing. It's not anything magical at all. It's not a new formula. It's actually exactly the same formula. We've just taken an extra step of subbing some stuff in. We sub into formulas all the time. So here's an example, a numerical example. So let's say we have 25 subjects, or participants. I believe the APA wants us to call them participants now. They have for, 20 odd years now. Yeah, roughly 20 years. A little more than that. I was once told to change the name of my subject section to participants, and I refused. I said they're pigeons. They did not sign up. Consent forms. I am not calling them participants. The editor was like, the APA wants to call them. I said to the editor, how about to call this section animals? Can I do that? He's like, yeah, it's okay. I said, good. Good. Now, whenever I do human stuff, I kind of want to call it a section called animals. So, you guys have been around first-year students. So 25 subjects are given an IQ improvement course, which isn't a thing. But I have IQ. I know the standard deviation and the mean of IQ in populations. So that's why I'm using this as an example. And their IQs are tested after the course. They end up with an mean IQ of 110. Okay. So, but that's it. Now, let's go back to that because it said something. I think it was saying there we go. I double clicked. No, why is it not? Now it's here on here, but not. Okay, it says the mean of the IQ is 100 and the standard deviation is 15, the variance 225. Okay, so we have a Z formula. We're just going to find that the probability of getting an IQ of greater than 110 with 25 people. X bar minus the 110 minus 100 over 15 divided by the square root of 25. I chose 25 for this example because it makes the arithmetic easy. 10 over 15 over 5, 10 over 3, which is 3.33. The probability of getting a Z greater than 3.33 is not in any of your tables that you have in textbooks because tables only never go to past 3. They just don't. However, my calculator does, and it tells me the probability of getting a Z of 3.33 or greater is 0.00043. Well, I guess this IQ improvement course works. There's a research design problem in here, I realize that. Right. It could just be that if we were sampling at a university, the average IQ of a university student probably isn't 100, it's probably close to 115. Just that's a guess, probably standard deviation for me. So it's probably not. We could do it, but let's pretend I randomly sample people from the population. Then this knows this is correct. So do you see what I did here? All I did is I just subbed the numbers in. And I would come to the conclusion, if our null hypothesis is that our mean should be 100, our alternative hypothesis would be it's not, and it ain't. 0.00043, 4/10,000ths of a percentage, 4/100ths of a percentage point possibility that I'm wrong. It just happened by random chance. Now, there's an issue here. We don't typically know sigma for a population. It's very rare. We can usually figure out what a population mean is, or some theoretical level we want it to be bigger than. We're great at that. That's fine. But figuring out variances is hard. I guess one could go back into all the literature ever done in a certain area and look at every single number and get a variance. I wouldn't do that. Well, we know the expected value of S squared is sigma squared, right? Because it's an unbiased estimator of sigma squared. Yes, this is true. We could just sub in S squared for sigma squared. right? Remember we just sub stuff into the Z formula? Well, why don't instead of the sigma, we just use an S? Do you see the logic so far?
No.
Well, we have this, which is, when I say this, I have to write it up here. We have this, and we then turn it into, for a sampling distribution of the mean, we turn it into this, because we're just subbing in. Okay? But we're not going to know this. But we can calculate that. And it's a guess at this. It's an unbiased estimator, in fact, of sigma. So why not just calculate it from the sampling? It's because it's a weighted guess. It's a weighted, well, it's not even a guess, it's an unbiased estimate. We know it's going to underestimate as much as it overestimates. Make sense there?
More.
Okay.
What's the second bullet there? Like, what, on the...
Oh, yeah. Well, the expected value of S squared equals sigma squared.
Okay.
Yeah. E with a brackets means expected value.
Okay.
Other questions? You with me so far? This is the logic that a guy named what's his name? Gossip went through when he figured this out in 19. But the problem is, if we just sub S squared in, that we know that not only does the mean, so we're dealing with a sampling distribution, but the variance, which is standard deviation. Now it's got a sampling distribution too, because we have to care about the sampling distribution of the variance. And it's going to change depending upon n. When we calculate variance, which is what we would do in this case, when we calculate variance, it depends on this, on the number of observations. The bigger they are, the bigger that number is, the smaller it gets. So now we have to take that into account too. Right? So now I have to take into account the fact that we have two sampling distributions. Not only the sampling distribution of the mean, which central limit theorem does a beautiful job, it gives us nice estimates, but we also have to take this into account. The sampling distribution of S squared changes depending upon n. Central limit theorem also tells us that variance is going to change depending upon n, so it should surprise us. The bigger the n, the smaller S squared is going to be. So we can't use Z. Z's assuming we know the population variance, we don't know it. But we're going to use something that is closely related to it. We're going to use the t-test using what's called the t-distribution. The t-distribution. Whoops, now that should get done. Let's go back. Okay, now I'm really annoyed. No, go back, I said. Oh, it's not showing up. This is really, really annoying. There's that, and then this.
Your header's kind of appropriate.
What, there's a problem here? It says, so we use T, but then when I try to make that come up next, it just goes away. So that's bad. So what I'll do is I'll just write it on the board. Go back. Okay. So, because I know what I have there. Boy, it's old timey. It's like I'm using a chalkboard. What year is this? So the t-test is for x. It's t equals x bar minus mu over s divided by the square root of n. The t-distribution was developed discovered by a guy named Gossett. He was a statistician for Guinness breweries. They have, quality control, that kind of stuff. And he realized this problem, and he fixed it by doing a bunch of math and discovering this thing called the t-distribution, which changes depending upon the number of observations, depending upon the degrees of freedom. So that's kind of neat that he discovered that. He published it under a pseudonym, the name Student. That's why you often hear it called Student's t-distribution. He published it under a pseudonym because basically Guinness didn't want people poaching their scientists. They were totally cool with their scientists publishing articles and feeling fulfilled and all that stuff. They said, you gotta use a fake name because we don't want someone from another brewery or someone else hiring you away. So he gets called Student for his contribution for statistics, but actually that's not his name. His name is Gossett. So all he's done here, I shouldn't say all he's done here, the logic of what he's done here is he's subbed S in for sigma. So instead of having the regular Z distribution, we've now got a T distribution. And that distribution changes depending upon the number of observations. So the critical value, the thing you have to exceed to get like less than a 5% chance, it's going to change depending upon the number of observations. So the obtained value, you do the math here, the arithmetic, you get a t-value and you see, is it bigger than the critical value? If it is, you reject the null hypothesis. It's really annoying that that's not showing up because it's really pretty on my page here. Questions so far? Do you see the logic of what Gossett did? He just subbed S in and he realized, well, the distribution, the probabilities are going to change depending upon the number of observations, and then he did a bunch of calculus and figured out what the critical values would be, or what the probabilities would be depending upon your observed, obtained t-value. Okay. So t changes depending upon the number of observations. And it's the degrees of freedom to estimate sigma squared. That's what it changes based on. So in other words, the degrees of freedom to calculate S squared. To be more precise, that's what it is. It's actually a pretty powerful technique. You don't actually have to know anything about population now. Yeah, you don't know the shape, you have to know the standard deviation. You have to know the population mean, but usually that's some theoretical value that you can just say, I want to make sure there are no more than, let's use a beer example, that each batch of Guinness is no more than, like, is it going to be more than 4% alcohol? Because Guinness is about 4.2% alcohol. So you put in 4.2 for beer, which is the percentage for Guinness. Okay? You're done. You don't have to know the standard deviation of every single batch of Guinness ever made. Right? Which is, I'm sure, vanishingly small, nonetheless. Because these things are heavily regulated. Not so much in the early 1900s. Okay, what if you have pairs of observations? You have pairs of observations. Things change a little. So we've got, I don't know, before and after. So in fact, if we did our IQ improvement thing, it's probably better to do it this way. We give people an IQ test before they take our little course where we steal their money. Because you can kind of change your IQ with taking the course. Doesn't work that way. I know I've taken 2 IQ tests in my life, and one when I was 9 and one when I was 22, and it's exactly the same score. It's literally exactly the same score. It'll go up and down. Yeah, sure.
Would you not be able to train someone for the specific
For a
test?
specific test, yeah, you could. You could do certain things. Like, for example, the WAIS, the Western Adult Intelligence Scale, has backward digit span. And in fact, in memory class yesterday, we were talking about how you can increase your digit span. You just practice. Most of the things in those tests are so esoteric that you wouldn't practice. Could you teach people to do better on a test? Could you actually improve their IQ or their intelligence? Almost certainly not. Right? Doesn't the world doesn't work that way. I wish it did. Like, I wish I could go, you're now all smarter. Can't really do that. You can all now do novel problem solving better than before. Give you $1,000. But yeah, could you train people in the test chart? This is one of the reasons there's so many subscales on those tests. IQ tests have a whole lot of subscales, right? Because you're going to vary in some things each day, but the overall score remains very consistent. IQ can go up and down a little, but it's not anything it's not like you go up a standard deviation or something like that. It just doesn't happen. It's pretty stable. And IQ tests are really pretty good, no matter what people tell you, they're actually really pretty good at estimating intelligence. Intelligence meaning what you do in school, how much money you make in your lifetime, like things that you think you correlate with. IQ's amazing that way. The dirty little secret that people don't like to know is that your IQ score correlates with a 0.6 with almost any success in life variable you can think of. Which is really sad because it goes against our whole nice Western liberal notion of we're all equal. We are all equal. We should all be equal opportunity. But some people are smarter than others. It's like some people can run faster than other people. Like, I think even Usain Bolt, if he never ever trained, could outrun me when I was that age. Because he just runs faster. Right? Not that I'm Usain Bolt in intelligence. That's not what I was trying to do. Please don't refer that. Okay. But for differences, if we did that IQ improvement thing, and let's say we weren't training people to do backward digit span, but you could train them up for the test. That is true. Well, in that case, we would have pairs of scores. And I could take all you guys and give you an IQ test, give you all the weights, right? And then I give you my little course, basically, which is improving your backward digit span. And I could probably teach you some logical reasoning techniques, things like that. And let's see, and then we're going to compare your scores after that. So now I've got differences of scores before and after. If there is no difference between the scores, what do we expect the mean difference to be? 0. So in fact, really that's not the formula. It's a little more complicated than that, but in essence, it is that. Because really what it is we're saying that we've got x bar minus mu over s divided by the square root of n, but mu here is 0, so it just becomes x bar over square root s divided by square root of n. Because the mu is 0. So that's the case, like I said, we can just say, it's going to be the same. We figure out some value, what's what I'm looking for, theoretical value for x bar. So in that case, now we get pairs of observations. Ooh, look at that. The 3D effect still works. I don't know what I did that for. But that's probably what broke the other part of the presentation. Oh, make it go in and out. This can be used for pairs of observations. Or with matching subjects. So I could match you, let's say instead of IQ, I'm going to do something else. I'm going to do a drug study. And I'm going to use some, I don't know, something that's supposed to lower your heart rate. Like lower your blood pressure. So we're going to measure, let's see, blood pressure. So I'm going to match people based on their blood pressure. So I measure all your blood pressures and I find out that Dana and Hannah have the same blood pressure. So you don't get the drug and you do get the drug. But I'm going to consider you one observation, like one subject in essence. And I'm going to take your score and subtract it from yours. And I'm going to say that Sean and Bryce are one other pair. And I'm going to give you the drug and not give you the drug. And I'm going to subtract your score from your score. You got to be really careful here because We've now made the subjects equal on this, so we can use this technique. They are now not equal on anything else, the group. So you've probably all learned about how random assignment to groups is really important, and it is. So this better be really a compelling reason. On the other hand, let's say you got twins. Let's say you got litter mates. If you've got like litters of rats, you can use this. That's not a problem. This is just a special case. This is often called a repeated measures t-test or a correlated t-test. Okay? Now, what if your pairs aren't matched, which is usually what we have? I don't know that I've ever used a matched pairs t-test. Oh, yeah, I have. Once. A long time ago. Yeah. There's one part of my PhD dissertation where I do that as a throwaway thing, group something, I can't remember. But that's once. And that was using the same observations from a bird before and after. Yep. One time. So if your pairs aren't matched, let's hope this comes up. Oh, good. No equation yet. This will come up. So maybe you have two populations. That, in fact, that's going to be your null hypothesis. I'm sorry, your alternative hypothesis is that your subjects come from two different populations. Your null is that they come from the same population. So your hypotheses look like this. HO, or HO, is mu1 equals mu2. Mu2, of course, my favorite band. And some people say they're just average, but that was a horrible reach. I'm very sorry. They are my favorite band. If you've seen my office, it's basically a shrine to you two. HA, is that mu1 is not equal to mu2. That's all our alternative hypothesis is here. There's no direction to it. We can do it directionally. It's not that big a step. But we're just going to say that two populations are not from the same, two sets of scores are not from the same population. So, I don't know what, there's one that it screwed up. I'll have to figure out what that is. So our original T formula is T equals x bar minus mu over S divided by root n. We have a statistic. We have our HO value for a mean, and we have an error. Let's just call it error. It's standard deviation. It's actually technically called the standard error mean. We wouldn't worry about that. Let's just call it error. Okay. So that's what we have, and now we just have to substitute values into this same T formula, which comes from the Z formula. Okay. So let's just figure this thing out. Well, the statistic comes from the thing that we're interested in. We're interested in what? X bar 1 minus X bar 2. The mean of group 1 minus the mean of group 2. So let's put that in for statistic. And then mu1 minus mu2 is there. Practically, actually, it's this. Technically, it's minus mu1 minus mu2, but again, our HO assumes they're equal. So mu1 minus mu2 should be 0. So, well, technically that's the formula. Practically, no one ever writes it that way. This is, again, why they all seem like different formulas, and they really aren't. Because we would confuse the crap out of you in 2126 if we also threw this in. There's usually like a bonus question on an assignment saying, the null hypothesis is the two groups differ by 5 points. Nobody ever does that. The world doesn't work that way. All right. So do you see how I went from here to here? And you see where the substituting in comes from? Okay? Statistic for HO, or statistic, I'm sorry, our null hypothesis, and whatever error is. Well, now we got to figure out the error. Variances have to be weighted because variances depend upon the number of observations. So the way we're going to weight them is by the number of scores to calculate. Right? That's just sensible. So s squared 1 over n1 plus s squared 2 over n2. That's going to give us a weighting, and then we're going to sort of a weighted average. You always add variances. You don't ever subtract them. Okay. So now the formula is this. T equals x squared, x bar sub 2 minus x bar sub 1 all over the square root of s squared sub 1 over n1 plus s squared sub 2 over n sub 2, and the square root of that quantity. Because that's our error. So really, it's all the same T formula. We've just put in different things for HO, for the statistic we're interested in, the test like the mean in this case, or subtracting 2 means, and for the error. But it's all the same thing. This is why we can always use the same distribution, like the probabilities of that distribution, to do a t-test. Questions? Okay. Okay, now, that assumed the variances were equal in the population, which we don't know. If the variances actually aren't equal, things change a bit. Now, you can say, how not equal? The rule of thumb is one variance 4 times bigger than the other one. That's the one that we take a look at and go, that's where the t-test kind of starts to fall apart, because one is 4 times bigger than the other. So one standard deviation being twice as big, or one variance being 4 times as big. Practically, what you do is you look at your data, we talk about exploratory data now, just look at your data and say, I see a difference here, and it comes up being not significant. Why? It's because you probably violated what's called the homogeneity of variance assumption. The variances are the same. So things change a little bit. We get this thing called s squared sub p, which is the pooled variance. So first we have to calculate that. And by we, I mean programmers at IBM that wrote SPSS. Right? You don't have to, I mean, again, if your calculator is variances and you're comparing 2 groups of 10, if you're me, you do it by hand because it doesn't take any time. Right? And you know the formulas. But this isn't hard to do with a computer, and hopefully I'll probably have time to show you quickly how to set up a t-test in SPSS. So we're going to weight it by the number of degrees of freedom, and then divide it by the n1 plus n2 minus 2. How many degrees of freedom are we going to look for when we look for the t-distribution table? How many degrees of freedom are we going to look at here? How many observations do we have? How many observations?
2.
N1 plus N2. There's N1 in group 1 and N2 in group 2. But we know we've lost degrees of freedom for estimating 2 things. So the 2 is close because the 2 is important. We have N1 plus N2 minus 2 degrees of freedom. So if we got 10 people in one group and 11 people in another group, we have 19 degrees of freedom. 21 minus 2 is 19. Right? We've estimated one variance by using N1 minus 1, N1, other one N2, and then we've lost a degree of freedom for each of those, with the X bars in there for the things we fixed. There are assumptions to make these tests work. Oh, before I say that, there is another way to do this that I don't know how to do like that. And that's called partial degrees of freedom. And you will see that sometimes on SPSS or any stats package. It does stuff that I don't know how through matrix algebra, because matrix algebra frightens me. So, who's done matrix algebra? Have you done matrix algebra? Okay. A couple of us are very unlucky people. It's horrible stuff. It's neat theoretically, but then when you actually have to do it, it's horrible. I hate it. It's the thing that almost made me quit graduate school. I can't do this. 24 years old, crying my homework. Still trying to figure out how I got the mark I got in that course. Got an A minus. Actually added up all the scores. Got a C plus. But C's are failed in graduate school. And that's when the prof said, I said, Ian, how did I get an A minus? Okay. I added it up and would you like a C plus Brodbeck? Because I can arrange that, it's not a problem. I said, no, I'll take the A minus. It's more of an empirical thing. I'm interested. How do you know what you're doing? Okay. It's a great moment. Don't worry, you're fine. All of us in our PhD stats class, that was the night of the Christmas party. So we had been drinking a little. And we all went back to the apartment, was it, I guess about 10 of us, and we all walked back, PhD 1, all walked back to the psych department, went to our mailboxes and pulled out our exams, and it had an exam mark, and then it said course grade. We were all like, the course grades have nothing to do with our exam marks. And we're like, okay, we should swear to secrecy. It happened every year. Pretty sure it happened every year. So there is this partial degree of freedom thing, which is probably more accurate than anything else. You never see it in publication. You never see it in print. I don't know why. Well, if you're lucky, the partial degrees of freedom agree with the pooled variance, agree with the not using pooled variance as far as the rejecting agent. There are assumptions to this test. All statistical tests have assumptions. You have a simple random sample. You can ignore that. As I said, because it's a central limit theorem assumption, we can ignore that. We can basically completely ignore it. Independence of observations you cannot ignore. And you're saying, wait a second, Dave, you said I could test before and after in the same subjects. Those aren't independent observations. Yeah, I know, but the individual scores you get are just differences, and those differences are independent of each other. When I say independence of observations, I mean if I know Bryce's score, I don't know Chris's score. It tells me nothing about what those scores are. Right? If I know Sean's score, I don't know Taylor's score. Right? It doesn't affect anything. I like to think of it sort of like it's like no cheating. So it doesn't matter where you sit, it doesn't matter what group you're in, the scores don't depend upon each other. If they're not independent events, all the math falls apart. Like all the calculus that's behind this that I'm not going to bother teaching you because I can't remember it. Yeah, I can't remember it, that's fair. It just completely collapses. The random sample thing's fine. Who cares? Independence of observations, the t calculation becomes literally meaningless. You may just randomly assign a number. 38. Okay, so they have to be independent. That's nice. You can calculate. You can take care of that with experimental design. So that's easy. This you have to worry about. Here's one, and I talked about homogeneity of variance, and why that would disappear. I'm so confused. Keynote's confusing me here. Homogeneity of variance says the two, if you have different groups, they have the same variance. Now, I talked before about how you can violate this to a point. So you have to have homogeneous variance, in other words, both groups have equal variance. However, one can be maybe as much as 4 times bigger than another one, and it's not a big deal. And there are ways to deal with violations of this assumption, and we'll talk about that, of course, after the test, but in a week and a half or so. But the interesting, and it's for a different test, but it's the same kind of approach. One of the things I can say about homogeneity of variance is that if you violate that assumption, it just makes the test more conservative. So at least you're not going to make a bunch of false positives, but you're going to miss stuff that was probably there. Right? So at least you don't make a fool of yourself and say, yep, you're psychics. So that's good. Violating that assumption makes the test more conservative. But the t-test is very robust when it comes to violation of homogeneity of variance, and robust beyond belief when it comes to violating the simple random sample assumption. So it's robust, it just means the robustness of the statistic is how easily it can handle a violation of its assumptions. And does it still work properly? So once on a quiz, when I had robustness as a definition, someone wrote the quality imparted to beer by using the choicest barley and hops. One, yeah, that's fine, correct. tell you also power, which is a good definition, right? Chance of rejecting a false null hypothesis. Right? Laurie Bloomfield wrote, "Power is what Dave has over us." I gave her a point too. I'm saying twice in my career have a joke definition I've given. Don't try, just know them. All right. Questions about this? Okay. What I want to do, I'd love to figure out why that screwed